This video is an example of Hess's law and how we could use multiple equations to calculate the enthalpy or change in heat or heat transfer of a single equation. I'm just going to jump right into the example. We are given three equations, and bear in mind that we're trying to find the heat change or the enthalpy of the above reaction, which states that 2 moles of carbon in a solid state plus 1 mole of gaseous hydrogen will yield C2H2 in a gaseous state, and again we're asked to find the change in heat or the heat transfer. Now, in this first equation over here, we're given that C2H2 in a gaseous state plus 5/2 of a mole of O2 yields 2 moles of carbon dioxide in a gaseous state plus 1 mole of water in a liquid state. And we know that the change in heat of this reaction, or the enthalpy of this reaction, is negative 1,299.5 kilojoules. Okay, so given the knowledge that we're asked to find the change in heat when carbon and hydrogen combine to form C2H2, we know that C2H2 must be on the product side of the equation, because C2H2 is shown on the product side in the initial equation above right here. And we also must know that carbon and hydrogen both must be on the on the product side, or on the reactant side of the equation, because they're shown to be on the reactant side in the equation above. Now, we know that the first equation that we're given here, C2H2, combines with 5/2 of a mole of O2 to produce 2 moles of CO2 plus H2O with a heat change of negative 1,299.5 kilojoules, has CO2 and H2O on the product side and C2H2 and O2 on the reactant side. So this might seem a little counterintuitive, but now we have to flip the equation to get C2H2 on the product side, because in this equation it's on the reactant side. And bear in mind that we're trying to get it on the product side because in the equation that we're asked to find the heat change for, C2H2 is on the product side. So in the first equation, just flipping it here, so the products become the reactants and the reactants become the products. So we know that 2 CO2 will now combine with H2O. 2 CO2 gaseous state will combine with 1 mole of H2O in the liquid state to produce C2H2 in a gaseous state plus 5/2 of a mole of O2 in a gaseous state. And remember that whenever we reverse the direction of a reaction, the heat change will always be the negative or the arithmetic opposite of what it was previously. So now delta H now takes on a value of positive 1299.5 kilojoules. Now let's see what we need to do to the second equation in order to conform to the form of the equation that we're trying to solve for. Now, we know that in the top equation we have 2 moles, not 1 mole of carbon reacting with hydrogen. However, in the second equation that we're looking at right here, we only have 1 mole. Simply, we just have to multiply both sides of the equation by 2 in order to get 2 moles of carbon to react. So multiplying both sides by 2, we would get 2C in a solid state plus 2O2 in a gaseous state to yield 2 moles of CO2 in a gaseous state. And remember that whenever we're calculating the enthalpy or the heat transfer, whenever we have twice the amount of reactants and products that we were discussing before, the change in heat must be twice, because the reaction is essentially being performed twice. So now, if we were to multiply negative 393.5 by 2, we get out my calculator here, 393.5 times 2, we would get negative 787 kilojoules. Negative 787 kilojoules. Now, in the third equation, we're given that H2 plus 1/2 O2 yields H2O. Now, we essentially don't have to manipulate this equation anymore, because we already have what we're looking for. We have 1 H2 on the product side, and we have 1 mole of H2 on the product side in the equation whose heat transfer we're trying to find. So we simply do nothing. And I'm going to write it again just so we line everything up. And again, the change in heat is negative 285.8 kilojoules. And again, remember that this still remains negative because the sign has not been switched because we did not reverse the reaction. Okay. Now we need to see what cancels out. Well, in the first equation, we have 2 moles of CO2 that are being put into the system. And we know that in the second equation, we have 2 moles of CO2 that are being produced or coming out of the system. So we know that these will cancel out because one is being put in and the other is being produced. One is being used up and the other is being produced. That's why they would cancel out. Now let's look at water. In the first and third equations, well, in the first equation, H2O is being put in, or it's being used up into the system, and H2O is being produced from the system. So these would cancel out because they're the same quantity on different sides of the reaction. Now let's examine what's happening to oxygen, or O2, in the gaseous state. Now, in the second equation, we know that 2 moles of O2 are being used up in the system. And in equation number 3, we know that additionally, a half of a mole of O2 is being used up in the system. So together, 2 plus a half totals to 2.5 or 5 moles of O2. And again, that's still in the gaseous state. So we have 5.5 moles, 5 halves moles of O2 being used up in the system. And we know that in the first equation, we have 5 halves moles of O2 being produced from the system. So these quantities simply cancel out as well. Now let's examine what we're left with. We have 2C in the solid state, 1 mole of H2, and these are our reactants, so these correspond to these values up here. And all we're left with on the product side is 1 mole of C2H2 in the gaseous state. And of course, that corresponds to the product side of the initial equation up here. So now we could think of the equation or the system as being balanced in this sense. So now that we have the equation completed, we know that Hess's law states that as a reaction undergoes several steps and several intermediate reactions, the final heat transfer is simply the sum of all the individual heat transfers. So all we have to do is sum up all of our delta H's. So we can think of this as delta H sub 1, delta H sub 2, and delta H sub 3. So if we were to total all these up, then the change in heat, or delta H total, would be equal to the sum, and if I get out my calculator here, we know that adding 1299.5, negative 787, and negative 285.8, if you were to think about this from my point of view, would actually be the same as taking 1299.5, subtracting 787, and subtracting 285.8, and that is exactly what we're going to do. So we plug in all of our values, negative 787, negative 285.8, and we get a total of positive 226.7 kilojoules. So the change in heat total is 226.7 kilojoules. And now we could conclude that because the heat transfer is positive, what we have is an exothermic reaction. And we know that this is an exothermic reaction because if you were to imagine that the heat is being applied to the product side, what we know is that 2C plus 1 mole of H2 plus 226.7 kilojoules of energy, so we know that energy is being taken from the system to produce C2H2. It's being released from the system off into the atmosphere somewhere. We could know we could think of that as an exothermic reaction because positive heat is being given off. And that is just one example of Hess's law.